Steps underlying the discrete Fourier series. In this video, we'll take some further examples. So this is example 3.11 from the course text. So you see the signal over here is a sinusoid with period capital N, and it consists of the linear combination of three sinusoids. Okay, and then there is a DC term as well. So naturally, it is periodic with period capital N, as can be seen from here. This cosine term is twice the fundamental. Okay, so you can see the fundamental frequency is 2 pi by n, and then it's twice the fundamental, and then there is a phase term. Okay, so fundamental frequency for this signal is 2 pi by n, so that's quite evident. So again, the signal is periodic with period n, so what we can do is to expand this indirectly in terms of exponentials. Why we are doing this is because we expand this in exponentials, it becomes very easy to compare this with the Fourier series expansion of x of n, and then you can easily by inspection see what the Fourier coefficients ak are. Okay, you see the expansion is in terms of the complex exponentials, so if you expand sine, cosine in terms of exponentials, then you can rearrange the terms. Okay, so for example, you can you have a DC term, so when k starts with 0, okay, this is a naught, so you can see that the DC Fourier coefficient is 1. Then when k is equal to 1, then this becomes a1 e of j 2 pi by n into small n, which is the discrete time index. So that's the fundamental. Okay, so if you collect the fundamental terms, which you can see over here, this is the fundamental term. Okay, this is the fundamental term. So you can collect 3 by 2 plus 1 over 2j over here. Similarly, so this becomes a1. Okay, similarly you can do the same for a minus 1, k minus 1, k minus 1. So this is k minus 1 terms. Okay, this is k minus 1, this is k minus 1. So you have the Fourier coefficient for k minus 1 over here. Okay, so this is a naught. So I'm just comparing this expansion of x naught of xn with the Fourier series expansion. So this expression of xn is in terms of exponentials. So this term is your a1. Okay, this term corresponds to a minus 1. Just look at the harmonic indexes, the k's. Over here k is 0. Okay, then k is 1 over here. So this k, we are looking for this k. So k is 1 over here. Then k is minus 1, which you can see. So a is also minus 1 over here. And then you can write this 2 pi by n as 2 into 2 pi by n, which is the second harmonic. So it becomes so over here this is k equal to 2, right? This is k equal to 2. Therefore this term, this Fourier coefficient is of a2, right? This is a2. This is for k equal to 2. Then similarly this is for k equal to minus 2. You see there is another exponential that gets multiplied. If you expand the cosine in terms of exponentials, this is ej 4 pi n by n into n. Then there is another term ej pi by 2. So you know ej pi by 2 is j, right? ej pi by 2 is cosine pi by 2 plus j sine pi by 2. So this is j. And if it comes with the minus sign, then it becomes minus j. So plus minus j pi by 2 is plus minus j pi by 2. Okay, so there is a minus sign over here as well. So you see this becomes minus j over here. So for a2 and a minus 2, a plus minus 2 is plus minus j by 2. Okay, so these Fourier coefficients, they can be easily seen by inspection. Okay, if you compare it with the Fourier series expansion, this is the Fourier series expansion, and this is the in this expression we have arranged the terms in a way how the Fourier series is expanded. So just comparing the Fourier series with the exponential expansion of sinusoids, you can write the Fourier coefficients directly. Now, an important thing is that ak is 0 for any other value of k. Okay, in the interval of summation in the synthesis equation, these Fourier coefficients, they are periodic. Okay, which means ak is ak plus n. Okay, what does this mean? This means that, for example, a naught is your an. The DC Fourier coefficient is going to repeat. Similarly, a1 to a of and plus 1. Okay, so the Fourier coefficients are also periodic, since in the expansion the discrete time exponential is periodic with period n, and these exponentials will be harmonically related with each other, and you don't need to go beyond capital N. So in the same manner, the Fourier coefficients are also periodic. They occur. They have a periodic nature, and the period of Fourier coefficients is again capital N. Okay, so Fourier coefficients are periodic with period n. So an is 1. Okay, which means over here an is a naught, and if you recall, a naught was 1 over here. So this is a naught, a1, a minus 1, and a2, a minus 2, and this goes up to dot 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 till a n minus 1. Okay, but the Fourier coefficients you see over here are 0 if for k greater than equal to 2, k greater than 2. Okay, but again, the range of vision for the harmonic indices, since you see the summation is limited to 0 to n minus 1, so we are considering the range of vision of k from I mean, this is limited, so okay, modulus of k is limited to n minus 1. So, or you can say that k is varying from 0 to n minus 1. Okay, there are capital N number of terms. So we are considering the n harmonics. So similarly, a3n minus 1 is 3 by 2 j1 by 2. Okay, so even you go beyond 3 periods, at the third period 3n minus 1 will be a minus 1. Okay, and what is a minus 1? A minus 1 is here. This is a minus 1. 3 by 2 minus 1 over 2j. Okay, so this is 3 by 2 minus 1 by 2j, which can be written as 3 by 2 plus j by 2, right? So I mean, why I'm doing this is just to show you that the Fourier coefficients for discrete Fourier series are periodic in nature, and you don't need to go beyond the period capital N because they tend to repeat. So it is sufficient to consider the Fourier coefficients in one period only. Similarly, a2 minus n, okay, it will be a2. Okay, so a2 minus n is a2. A2 is what? J by 2, right? A by 2 is J by 2. This is A2. This is your A2. This is A2 coefficient, J by 2. So in the figure below, we plotted the real and imaginary parts of these coefficients for capital N equal to 10. The period is 10, while the magnitude and phase of the coefficients are depicted in the next slide. So over here you see these are the real parts of the Fourier coefficients. These are the Fourier coefficients, okay. And a naught is 1, okay. Then the real part of a1 is 3 by 2. So you can see on both the sides, so 1 and minus 1, you have the real parts. And for a2, there is no real part, so it comes with 0, okay. And this thing repeats at capital N as well. So this thing is over here as well, and then it repeats at 2 as well. Similarly, minus n, minus 2n, and this goes on repeating itself. Imaginary parts, you see for DC there is no imaginary part, but however for the first harmonic this is 1 over 2. For the first harmonic this is first harmonic. This is first harmonic, and this is the minus 1. So at 1 this is minus 1 over 2. You can see over here, okay, the imaginary part. Then minus 1 for k minus 1. This is plus 1 over 2. So it's above that. It's above the k axis. And then you are left with plus minus 1 over 2 for a2 and a minus 2. So this is 2, this is minus 2, okay. And these imaginary parts are also repeating at the period capital N, and this continues at 2n and 3n, and it continues so on and so forth. So these are the magnitudes magnitude and phase plots, and you see again this the magnitude and phase plots are also repetitive, they are periodic, and for example a naught has a magnitude of 1, then this term has a magnitude of, for example, under root 10 by 2, so at plus minus 1 you have the magnitude of under root 10 by 2, and then for a2 the magnitudes are 1 half, which can be seen over here. So these are again the magnitude of the Fourier coefficients, and these magnitudes are repeating. For the phase part, you see for the phase of the DC is 0, so there is nothing over here, okay. But again, for example, plus minus 2 is going to contribute a phase of pi by 2, okay, so plus pi by 2 and minus pi by 2, and then there is a phase at plus 1 and minus 1 over here as well, okay. So again, the idea is that the Fourier coefficients for discrete Fourier series are periodic, which was not the case in continuous time Fourier series, okay. So these are the differences, and again you see the other thing is that we don't have any convergence problems because the series is finite in nature. This series, the Fourier series, the discrete Fourier series, is of finite nature, so it is always convergent. It's a finite series. So another thing to note over here, if you look at the Fourier coefficients, they are in conjugate symmetric, okay. Well, it's not hard to see that AK is A minus K star, right? And why does this occurs? Because X of n is a real signal, right? X of n is a real signal. It's not a complex signal. And for real signals, the Fourier coefficients are in conjugate symmetric. This is, I mean, we have already shown this in the if you look into the properties of continuous time Fourier series that we discussed in the previous videos. For a real signal, the Fourier coefficients are in conjugate symmetric. If and again, if your signal is even, then your Fourier coefficients are also even. That is, AK will be A minus K. If your signal is odd, then that implies that the Fourier coefficients are also odd, and they are purely imaginary, okay. But over here they are not purely imaginary because the signal is not odd, it's not completely odd, and it's not completely even as well. So because but it is real. If it is real, then the Fourier coefficients are in conjugate symmetry. So you can see A1, the coefficient of A1 and A minus 1 are in conjugate symmetric. Okay, you can take the conjugate of A1 to show that this is equal to A minus 1. Similarly, A plus minus 2 are in conjugate symmetry. Okay, so this is because X of n is real. Okay, this is because X of n is real. So so this is what we have seen before for the real time, for the continuous time Fourier series signals as well. Okay, so this applies for the discrete time sequences as well. So X of n is real. Okay, so note that in this example 3.11, A minus K is AK star for all values of K, and in fact this equality holds whenever Xn is real. And it's a very similar, I mean the parallel is the same for continuous time signals. Okay, so let's take another example. This is 3.12. So in this example, if we consider the discrete time periodic square wave as shown below, you see the square wave is taking the values of 1 from interval minus n1 to plus n1, and then this is periodic at period capital N. Okay, so it's repeating itself. So we can evaluate the Fourier series for the signal because X of n is 1 for the given range. So it is particularly convenient to choose the length of n interval of summation in Fourier series so that it includes the range. Okay, so in evaluating the Fourier coefficients, if we do this over the range of the signal X of n, where it is non-zero minus n1 to plus n1, this is 1 over n. This is the expression that we derived for the Fourier analysis of the coefficients. Okay, so this is X of n e to the minus jk 2 pi n by n, and since X of n is 1, so you don't need to write explicitly for X of n over here. A minor substitution is going to show you that this series become a geometric progression. Okay, so if you substitute for small n and make this summation over m. M is another integer variable. Then this becomes the lower index starts with for minus n, it starts with 0 and then it goes to plus 2 and 1. Okay, so you can take this over here. This n is going to be substituted by m minus n1. Okay, you can take n1, since you can bifurcate this exponential into 2. You can take n1 out. The summation is over m. This does not contain m. Now you can see that this summation, and looking at the indices of the summation, this is a geometric progression. Okay, so if you are going to solve this, the Mock summation consists of, first of all, 2n1 plus n terms. Okay, because it starts with 0, so there are going to be 2n1 plus n terms, plus 1 terms. So this is in geometric series, which can be evaluated from a geometric sum. So this yields there are 2n1 plus 1. So this is 1. This is the common ratio of the geometric progression. Okay, because the first term is going to be e minus first term is going to be 1. Then there will be, for m equal to 0, for m equal to 1, this will be e minus j 2 pi by capital N. Okay, so this is the ratio, e minus j k 2 pi by n, right? And this continues. Okay, the second will be, for example, e minus j k 2 pi by capital N into 2. Then it will be e minus j k 2 pi by capital N into 3. Okay, so it becomes a geometric progression, and you can use the geometric progression formulation. It's like 1 minus r of n. N is the number of terms, or 1 minus r. Okay, the first term was 1. Okay, so you can write 1 over here as well. So this is r is the common ratio of the terms, which is over here, e minus j k 2 pi by n of the series. And then you can rearrange this into a sign by sign form. Okay, and you can see this is not valid for k equal to 0 or plus minus n plus minus 2, and it takes a 0 by 0 form. So you solve this by L'Hopital to show that ak is equal to 2n1 plus 1 over n for k equal to 0 plus minus n plus minus 2n. Now if you plot this for certain time periods, let's say capital N equal to 10, 20, 40, and the coefficient for 2 and 1 plus 1 equal to 5, and these are the periods. So n equal to 10 is for part A, part B, C. You see that the form is a sign by sign of the Fourier coefficients over here, and this index is over k. So for example, at k equal to 0, this takes the form of 2 and 1 plus 1 over n, and for the first figure the period is 10, and this is 5, so 5 by 10 is half. Okay, so the first the DC coefficient, Fourier coefficient, is half, and this tends to repeat itself at capital N equal to 10 and minus 10. Okay, so the same thing continues. This is n equal to 10, right? N equal to 10, and then this is equal to n. This is equal to n equal to minus 10, right? Similarly, then after that, if when your k is not equal to 0, k equal to 1, 2, and 3, so it takes a form of sign by sign. So the coefficients are dictated by the sign term. Okay, so it goes like this. So these are the samples. You can think of them as the samples of sign by sign. And again, if you consider this in part B for n equal to 20, this 2 and 1 plus 1 is 5. So 5 by 20 is 1 quarter. Okay, so it's still less than that. And then if you consider for 40, then 5 by 40 is 1/8. So over here it's 1/8. And then again, this thing repeats. Okay, so the Fourier coefficients are again periodic in nature, right? And they take the form of sign by sign, right? So for different periods, it's plotted as such, and they are the period is different. Okay, so you can see the effect of increasing the period. So for example, over here, this is n equal to 40. So after 40 samples, it's going to repeat itself. After 40 samples, it repeats itself. This is the repetition occurs for n equal to 20 over here. This is for n equal to 10, so they are much bunched together. So again, the idea is to show that the Fourier coefficients are periodic. Okay, so these are the Fourier coefficient of a periodic square wave. For any arbitrary periodic sequence, Fourier coefficients are periodic. So this is, for example, 3.12, and these are the plots for 3 different periods. Okay. And another thing that you should notice over here is that you see this square wave is real. Okay, so x of n is real. X of n real means that your Fourier coefficients are going to be symmetric, which is the case over here as well. The Fourier coefficients are all symmetric, and in fact you can say that they are there in conjugate symmetry. Okay, they are also in conjugate symmetry. So why they are real and symmetric? Because the signal is real. Okay, the signal is real. Also, you can say the signal is even. Okay, so you can say that this is x of n is x of minus n. So this is going to imply, the implication that it's going to have on the Fourier coefficients is that the Fourier coefficients are going to be real and symmetric. So I'm not putting the steric star. They're real. So that means AK is AK star. So we have not seen any imaginary Fourier coefficient. Okay, so they are real and they are symmetric, right? So for example, over here, this is real. This quantity is real. The Fourier coefficients are all real. We don't have any complex quantities in the Fourier coefficient, so there are no complex quantities. Also, they are symmetric. Okay, they are also symmetric. So you can see the Fourier coefficients for all these three periods. The Fourier coefficients are symmetric. Okay, so you must understand. I mean, there's a very strong analogy between the continuous time Fourier series and the discrete Fourier series. If you wish to have a look on the properties of discrete time Fourier series, there is a table 3.2 in your course text, and these properties they can be derived in a very similar manner as what we did for continuous time Fourier series. So we're not going to derive them over here. You can just stick to the definition of discrete Fourier series, and if you wish, you can, for example, you can show for linearity, because the discrete Fourier series consists of summation, and summation operation is a linear operation. So if, for example, if you have a linear combination of two sequences, then the Fourier coefficients is again the linear combination of two sequences. Okay, where AK are the Fourier coefficients of x of n, and for the sequence y of n, we have the Fourier coefficients of bk. Okay, k being the harmonic index. So again, you see for time shift, they take a very similar form of as what we derived earlier for continuous time Fourier series. So we're not going to do this again over here. Have a look at the table and see the similarities for yourself. For example, if the sequence is time shifted, then there's an exponential. So there comes an exponential that multiplies with the Fourier coefficient, which is e minus jk 2 pi by n naught. Again, it also implies that the magnitude of the Fourier coefficients, it stays intact. Okay, I mean, time shifting a sequence implies that the magnitude of the Fourier coefficient stays the same. That is, the strength that that harmonic is contributing, the kth harmonic is contributing into the sequence, is the same. Okay, it has to be the same, because time shifting doesn't imply you are contributing the waveform. Actually, the waveform stays preserved, so therefore the number of harmonics are there are same number of harmonics are there, and their strengths, they should be the same. Okay, this is the intuitive meaning behind the time shift. The strengths of the harmonic or the Fourier coefficients are not changing. Okay, but there is a phase term that is coming over here due to the time shift. So if you frequency shift, for example, now if you multiply an exponential over here, then you will have instead of k, you will have k minus m. Okay, you simply shift in the you will have the shift in the harmonic index instead of n, so there will be k minus m. Similarly, if you take the conjugation, then it will become a minus k. Okay, time reversal is a minus k. Similar, they're all very similar to what we have in continuous time. For example, if for x minus t it was a minus k. Okay, so flipping a sequence or a signal implies flipping the Fourier coefficients, but again the magnitude stays the same. Flipping does not mean that you are going to introduce new harmonic content. The magnitude of the harmonic stays the same. Okay, and then some of the properties are, for example, are important. For example, multiplication will involve convolution of the Fourier coefficients. Okay, and this convolution will be of circular nature, because your series is finite. Okay, so whatever, no matter what you do, since the harmonics are limited from 0 to n minus 1, you are considering, or capital N number of consecutive k terms, your convolution sum is also going to be the same, no matter what consecutive range for k you select. Okay, so if you multiply two sequences, the Fourier coefficient, the resulting Fourier coefficient will be the convolution, will be a circular convolution of the Fourier coefficients. Okay, so you see it uses the word periodic convolution. So if you have a periodic convolution, for example, over here, then you have, and then you have a multiplication of the Fourier coefficient. So it's vice versa. If you have a convolution of two sequences in time domain, then it means, well, it's also in the time domain. The Fourier series is also in the time domain, but we're looking at the effect of that process on the Fourier coefficient. The Fourier coefficients they get multiplied. Okay, and multiplication of two sequences means convolution of Fourier coefficients. Okay, so if you see over here, for example, the first difference, you can just use linearity property and the time shifting property. So for example, over here, this is e minus 1 minus e j k 2 pi n into 1 ak. So this first difference and running sum, they can be evaluated by invoking the first few properties. Okay. Similarly, for the conjugate symmetric for real, if x of n is real, that we were discussing before, then you have the Fourier coefficient, they occur in conjugate symmetric. Okay, and the real part of ak is real part. The real parts are the same. Imaginary parts, they occur in the odd manner. So imaginary part is minus. So basically, they're in conjugate symmetry. This is what is being implied by this term. The magnitudes, they stay the same. The phases are odd. Okay, the phase has to be odd. Magnitude stays the same. So if the signal is real and even, it's both real and even, then that means AKs are both real and even. If xn is real and odd, then that means AKs are purely imaginary and odd. Okay, so even and odd decomposition follows from these properties. Okay, even decomposition is the real of AK, and the odd decomposition implies the imaginary part of AK. So then finally, the Parseval relation for periodic signals gives you it relates the energy content of the sequence in one period. Period is capital N. So if x of n is periodic, then in one period, how much energy is there can be expressed in terms of the Fourier coefficients, because the Fourier coefficients are the harmonics of the Fourier series. So to evaluate the energy, you can use the Fourier coefficient. So if you have the Fourier expansion, then the magnitude of those harmonics is the energy content, is the energy content itself of the signal. So the strength of the harmonics reflect the energy that each harmonic is contributing in the sequence. Therefore, if you sum up this magnitude squared of harmonics, it becomes energy of sequence in one period. Okay. So let's use these properties. This is another example, 314 from the course text. So suppose that we are given the following facts about the sequence x of n, and what it says is the first fact is that x of n is periodic with period n equal to 6. So if that is the case, then if I have to write the Fourier analysis equation to determine the Fourier coefficients, I can do that from n equal to 0 to 5. So there are, you see, 6 terms. Again, the series is finite, consisting of capital N number of terms, 6 terms. So this is my Fourier analysis equation to evaluate the Fourier coefficients for the given k. Okay, and it's given that over one period, the sum of the samples is 2. Okay, so what it means is that if I substitute for k equal to 0, if I make this k equal to 0, then this summation becomes 1 over n sum from n equal to 0 to 5 x of n, right? So what does this mean? This means that we are looking at which coefficient, which is looking at the DC coefficient of Fourier series, A naught. So we can use this information over here. Capital N is 6, so this is 1 over 6, and this sum is given in the fact 2, that this is equal to 2. So your DC Fourier coefficient is 1 over 3. It comes out to be 1 over 3. So from fact 2, all the information that we can deduce, we can understand, is that the DC Fourier coefficient is 1 over 3. So if k equal to 0, then expanding this simply means summing up the samples, and summation of samples of the sequence x of n over one period is given as 2. So 2 by 6 is 1 over 3, which is the DC coefficient of Fourier series. Okay, let's look at the third fact. It says, again, over one period n equal to 2 to 7, minus 1 n to x of n is 1. Well, you have to look at in a more close manner for this. For example, well, what we have to understand, which Fourier coefficient is this fact implying, and what is the value of k. So what if for this expression, if we write k as 3, and then let's try to write this as 1 over n. It doesn't matter if your summation starts with n equal to 0 to 5. Well, we can also start this from n equal to 2 to 7 without losing any, without any loss of generality. It's again one period. So this is x of n. Then we can write this as, well, how to write minus 1n is, you see, minus 1n can be written in terms of exponentials as e j pi n, right? Because cosine pi is minus 1, sine pi is 0. Also, we can write this as e j 3 2 pi by 6 into n. Well, the motivation for writing this is that I have the exponential in this form. Okay, so you can see over here, you can write the minus as well over here, no problem. So if I write this as exponential minus j 3 2 pi by 6, because n is 6, we're considering 6 terms. 6, this is 6, I guess. Then n, then there is a discrete time index. So you can see, if you compare this Fourier coefficient with ak, you can see k is equal to 3. This is k equal to 3. This is k is 3 over here. K is 3, and this is the third harmonic. So we are evaluating the Fourier coefficient for the third harmonic, and what we are given is that this can be written as, so n is 6, so you can write this as 1 over 6, and this term is x of n. Basically, this term is minus 1 over n. This term is minus 1 over n, and summation of minus 1n into x of n is 1. So your Fourier coefficient for A3 is nothing but 1 by 6. That's it. This is what fact 3 implies. Okay. So you see, if we determine, let's determine the sequence n, and we have to determine the sequence n from these 4 facts. So we denote the Fourier series coefficients of x of n by ak, and from fact 2 we conclude that a naught is 1 over 3, because we use this information for k equal to 0, and we evaluated a naught as 1 over 3 because the summation of samples were given. Then we noted that minus 1 over n can be written as e minus j by n, which can be further written as e minus j 2 pi by 6 into 3n, right? And if you plug this inside the summation, then you can see that k is equal to 3. Okay, so fact 3 means A3 is 1 over 6. A3 is 1 over 6. Then the fourth fact, so we have, now we have 2 Fourier coefficients. The fourth fact says that x of n has the minimum power per period among the set of the signals satisfying the preceding 3 equations. So what is the minimum power that we can have? Now, you see, if you expand x of n in terms of Fourier series, its Fourier series is of the form summation ak Fourier coefficients. Summation is again over k, okay, and this is for one period. This is one period, and this can be written as e j k 2 pi by n small n. Okay. Regarding the power, you understand that from Parseval's relation, this is Parseval's relation, it shows that the magnitude squared summation of the Fourier coefficients gives the energy of the signal in one period. But this is, since this is being normalized with 1 over n, and this is the power in one period. Okay, so the minimum power requirement from, so this is the Parseval relation. Okay, and we are including all the Fourier coefficients. Since each non-zero coefficient will contribute a positive amount to P, that means besides A0 and A3, A1, A2 and A4, A5 are going to contribute non-zero power, and since the values of A0 and A3 are prescribed, the value of P is minimized by choosing A1, A2, A4, A5 equal to 0. So then it follows, well, you see the fact 4 is important in establishing that A1, A2, A4 and A5 are all 0, because we are looking for the minimum power. Since we have from the preceding facts, this implies A0. Okay, from the preceding conditions, we already have non-zero Fourier coefficient, the DC Fourier coefficient, and third harmonic Fourier coefficient. So to have a minimum power, we have to set the other coefficients to 0. For the minimum power requirement that satisfies the above requirements, the other Fourier coefficient should be 0. So you have to set A1, A2, A4, and A5 equal to 0, so the minimum power is contributed. And then it follows, if you expand the summation, the first term will be A0. Second term is 0. Okay, first term, I mean, for k equal to 1, A1 is 0, then A2 is 0, then only the non-zero term in the summation, the next non-zero term is A3, then it will be of form E of j 3, 2 pi by 6, 2 pi by 6, this has to be multiplied by n, okay. And what is this again? This becomes ej pi n, right? So A0 is 1/3 plus A3 is 1/6 into, this becomes -1 power n, right? Because this becomes ej pi n, so this is -1n. So this is the expression that we have. This is what? This is x of n. Now if you put the values for n, you can compute the sequence. So for n equal to 0, for example, this is 1/3. This is 1/3 for n equal to 0. Then for n equal to 1, this will be 1/3 minus 1/6. Sorry, this is not 1/3. For n equal to 0, it will be 1/3 plus 1/6. So I have to add 1/6 to it, which means, what does it mean? It means 2 over 6 plus 1 over 6 is 1/2, right? This is 1/2, sorry, this is 1/2. Not 1/3, 1/2. Then for n equal to 1, this becomes 1/6. This is 1/6. This is indicated. Okay. And for n equal to 3, it continues. Okay. So for n equal to 3, this is again equal to 1 over 6. Okay. For n equal to 3, this is going to be -1. So 1 over 3 minus 1 over 6 is again 1/6. So this 1/6. This is 1/6. So it continues like that. You have to put the values for small n to compute the sequence itself. And this is sketched in figure 320. You can see over here as well. We have the samples. For 2, it will be 1/6 plus 1/3, okay, which will be again 1/2. Okay, so this value is 1/2 over here, which occurs at -2 plus -2, which is 1/2. So this is the sequence, and it continues. Okay, and you also see that this sequence is of periodic. It's given as it's periodic, and this sequence is going to repeat itself at capital N equal to 6. Okay, so for example, at capital N equal to 6, it will be A0, which is 1/2. Okay, so A0 is going to be equal to A6. Similarly, A7 is going to be A1. So this trend continues. Okay, this trend continues. That's all.